In this video, we're going to continue the lesson on stoichiometry with the ideal gas law. We're going to do example 3 now, where we have a limiting reactant problem. So let's go ahead and start reading. How many liters of CO2 will be produced at 25 degrees Celsius and 150 kPa when 8.77 liters of CH4 react with 15.9 grams of O2? So first of all, before we even dissect this, let's just write out an equation. So we have CH4 gas reacting with O2 gas. And remember that O2 is a diatomic molecule, and that's why it's gas. So we put it as gas there. And it's going to give us some CO2 gas. We're going to say it's a complete combustion plus H2O gas. And it looks like we need another 2 more hydrogens there. We have 4 oxygens total, so 2 here. So it's going to be 1 here. Okay, so now it's nice and balanced. So our first step is writing out our balanced equation. Then we're going to go ahead and write down some information that we have. So for oxygen, we're given that we have a mass of 15.9 grams. And for CH4, we are given that we have a volume of 8.77 liters. And now we are looking for the volume of CO2. Now it's a gas, and we have a bunch of stuff given to us. We have the pressure given to us is 150 kPa. We have the temperature given to us. It's 25 degrees Celsius, but don't forget it has to be Kelvin. So that's going to be 298.15 Kelvin. We also have the R constant, as usual, 8.314, and with its units of kPa liters over mole Kelvin. And we want to find the volume. And so to find the volume, don't forget we need the moles. And to find the volumes, remember that the equation is PV is equal to nRT. So the volume is going to be volume is equal to nRT over P, but we need N first. So to find N, we have to use a mole ratio. We have to use a mole ratio between one of the reactants and the CO2. And so you'll notice is the problem in this situation is we're given information about both reactants. We're given sort of possible quantity information about the CH4 and the O2, and we need to decide which one we're going to use in the mole ratio to find the CO2. In other words, we need to determine our limiting reagent. And so I'm going to write out a couple things here. Step 2 is going to be to find the number of moles of each reactant. So let's do that. We're going to find the number of moles of each reactant. So for this one here, the number of moles is equal to mass over molar mass. And that's going to be the 15.9 grams over the 32.00 grams per mole. And that's going to give us, let's do that here, 15.9 divided by 32. We get 0.496875 moles. Okay. And now we're going to do the same thing. We're going to find the moles of CH4, though, but this time we can't use the molar mass because we have the volume here. So we can find the moles of CH4 by using our PV is equal to nRT. It's a gas, so that's how I know I can use that. Don't use PV is equal to nRT if you have a aqueous solution, or if you have a solid, or if you have a liquid. Don't use that. Only if you have a gas, you can do that. So in this case, we're given the volume. And so we can find the moles by doing N is equal to PV over RT, which is we have a pressure given to us. So 150 kPa times the volume, 8.77 liters, over the RT, so 8.314. And the units you can see are over here, so you can write those in and try to cross those out yourself as practice, times temperature, which was 298.15 Kelvin. And so we'll do 150 times 8.77 divided by 8.314, and then divided by 298.15, and I get 0.530696 moles. So now what I have to do is I need to find my limiting reagent. I have to compare the moles of the O2 and the moles of the CH4. And you can use any method that you want. I'm going to use the method one we discussed, where we divide both by their coefficient, and then we compare to see which one's smaller or larger. So this one's divided by 1, and I get 0.53069629. And this one over here is divided by its coefficient of 2. So 0.496875 divided by 2, and I get 0.24844375. So it looks like CH4 is larger than the O2 once through its division. So since the CH4 is larger than the O2, that makes O2 is the limiting reagent. And so that's just an extra step I had to do here. Now everything else is going to be the same. I can now use the limiting reagent, the moles of the limiting reagent, not the one that I divided by 2 here, but the actual moles limiting reagent that I have in the question. And the mole ratio between the limiting reagent and the CO2 that I want to find the moles of CO2. So we're going to do that the moles of CO2 is equal to the moles of O2 before you divide it by 2 there. So 0.496875 moles times, let me write down the ratio actually, so it's 2 O2 for every 1 CO2 times, we want to get, I should put moles of O2 here. Let me just erase that to make it nice and neat. Mole O2 times 1 CO2 for every 2 O2. You can cross O2 out, and you get 0.24844375 moles of CO2. And now that we have the moles of CO2, so let me just write that here, 0.24844375 moles, I can go ahead and find the volume by using this equation over here. So step 5, V is equal to 0.248 I'll put, but all my numbers are still in the calculator, so 0.248 moles times 8.314 kPa liters mole Kelvin times the temperature was 298.15 Kelvin. Cross Kelvin out, cross Kelvin out, cross moles out, cross moles out. Don't forget to put over the pressure, which was 150 kPa. Cross kPa out, and you're left with volume in the end. And so we'll do that times 8.314 times 298.15 divided by 150, and we get 4.105544134 liters. But don't forget we have to follow the proper number of sig figs, and it looks like 2 significant digits is what we need, because there's 3 and 2, 2 is smaller. And so we can say, therefore, the volume is approximately 4.1 liters of CO2. So really what we did here is we first, so if we were to summarize, summary, we, one, found mole of each reactant. Two, we found the LR. Three, we used mole ratio and LR to find the moles of desired moles. And then four, we converted to desired value, which in this case was volume. And really, it's like any other limiting reagent problem, except we had to use the PV is equal to nRT because we had a gas and we were given its volume. And so we could use that to find the number of moles there. But it's the same as doing a limiting reagent problem for concentration, for just regular old mass, and that's essentially it. After you find a limiting reagent, it's just a basic stoichiometry problem. In the next lesson, in the next video, we're going to finish up the last two examples, but feel free to try them yourself first, and then check with my video to see that you're on the right path.